about static electricity, and we're saying it's all because static electricity happens because the electrons around the outside of an atom and the protons and neutrons are stuck in the middle, so they don't move. It's the electrons that move. So today we are going to look at current electricity. Get your booklet out and open onto page 4. And current electricity is still movement of electrons, but static electricity tends to be electrons building up on something, whereas current electricity is electrons constantly moving in like a current of water. Okay, so electric current is the movement of negative electrical charges, so electrons, in a circuit. So generally, and you will be playing with electrical components next lesson. Generally, what you have is you have something like a battery or a power supply that provides the energy to the electrons to move around a circuit. You have wires. They're usually made out of copper because copper is a good conductor, allows electrons to flow through it. And you have something like a load. We call it a load in the circuit. You have something in the circuit. Usually we look at lamps because they're quite easy to use. Connected back up to the other side of the battery. So the battery provides the energy for those electrons to move, and the current is that flow of the electrons around the circuit. Okay. So an electric current is the movement of electrons. So electrons we know that they get repelled away from the negative. So from the negative and towards the positive terminal. So in a battery, electrons basically move in this direction. Quite often people think, oh, is it electrons like coming out of the battery and moving around? So basically what it is, the electrons all exist, like electrons exist in the wires, but when you connect them up to a battery, you give them the energy to start sort of passing their energy along. So it's a bit like a conga line where the front is attached to the back, and you kind of like they shuffle along, they've got the energy. It's not like one electron like that. It's a big conga line of electrons. Just to point out that in a circuit diagram, the positive side of a battery is the long side and the negative side is the short side. So, for a current to flow, 2 conditions must be met. There must be a complete conducting path. That means a wire from the negative to whatever's in it, then back up to the positive. So a big circle, basically. And there must be a supply of electrical potential energy. You've called it electrical energy up till now, but the fancier word, the fuller word is electrical potential energy. We'll go back to just calling it electrical energy, though, normally. So materials that allow negative charges to move through them easily are called conductors. Does anyone have any examples of conductors? I've said one already. Yeah. Copper, yep. Anything else? Basically any metal, so aluminium, basically any kind of metal is good at conducting, because metals, the structure, if those of you that do chemistry, might have talked about the metallic structure having electrons that are free to move. So metals are good conductors, and also there's a type of carbon that's a good conductor. Anyone? Yeah, graphite. That's sort of the only real non-metal you need to know that conducts electricity. And materials that do not allow negative charges to flow through them easily are called insulators. Not to get mixed up between insulators of heat, but I suppose it's the same kind of thing. It doesn't allow heat to flow through them, it doesn't allow electricity to flow through them. And some examples of insulators could be basically most things, yeah. Wood, yeah. Plastic. As you get around the outside of wires, you get plastic so it doesn't shock you whenever you touch the wires. Lots of different things could be insulators. Generally, we use plastic to coat anything that is a conductor so it doesn't, shock us. Okay. So just at the bottom of that page, you should have a little bit of space. I just want to write a little summary of current and voltage because it's quite the definitions of these come up quite often in exams. So current is the flow of charges, which is flow of electrons. So it's that movement of the electrons moving around. And voltage is the energy given to these charges. So the higher the voltage battery, the more energy those charges have. And by charges in this point, we're usually just talking about electrons in circuits. Yep.
The batteries basically just pushing the electrons back.
Yep.
So why is it when you get a wire you get two ends?
You mean if you just had a wire and you had no battery, why would they not flow? Because they haven't been given any energy, so they can't. It's basically if we haven't fed you for like 3 weeks, you wouldn't move very far. Yeah. So you might get in very rare instances, you might get some movement of electrons. Sometimes electrons just move on their own anyway. But if you want a nice ordered movement of electron, you have to have something pushing it round. Okay, so electrical charge. The size of the charge on a proton is equal to the size of the charge on an electron, but has the opposite sign. Okay, and we know that because neutral atoms have the same number of protons and electrons. They sort of cancel each other out. Electrical charge is given the symbol Q, just because you might get it mixed up with other things that begin with C, and is measured in units called coulombs. That's capital C. It's actually named after somebody, Mr. Coulomb, Professor Coulomb maybe. The charge on an individual electron is very small. So the actual charge on an electron or a proton is 1.6 times 10 to the minus 19. And remember standard form, that means 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 To find out how many electrons would be in a certain amount of charge, you would use this. So number of electrons, that's my shorthand way of writing electrons. So if you were given like 3 coulombs, to find out how many electrons were in that, it'd be the charge divided by the charge on 1 electron. Alternatively, if you wanted to find the overall charge of a certain number of electrons, you would say the number of electrons times by the charge on 1 electron. Okay. So there's a question there, how many electrons would be required to make a total charge of 1 coulomb? So you'd use this top one here, number of electrons equals the total charge divided by the charge on 1 electron, so 1.6 times 10 to the minus 19. So can you work that out, please, on your calculator? Just going to test that you're happy using your calculator. You can try, although it's probably not going to be great with the little numbers. The charge is just 1. So basically, I'm just testing you putting that into your calculator. If you are using your phone calculator, it's probably not going to work very well. you should get that number. If you don't get that number, let me know and we can have a look at your calculator skills. Remember the button, the E button, the bottom is your 1.6 E minus 19. Everybody got it? It's really important that you do get, used to putting in these numbers, the standard form numbers, because you'll use them loads. And phone calculators tend not to be very good at putting in standard form numbers. Did you get it? Right, so electric current. So current is the movement of those charges in the circuit. So electric current is given the symbol I, because it's named, I think it's for something French. I'm not entirely sure what the French word is. And it's measured in units called amperes, after Monsieur Ampere. A current of 2 amperes is written to capital A. Okay, and it's capital A again because it's named after a person. So electric current is a measure of the amount of charge that flows past a point in 1 second. So the rate of flow of charge. So that's really important. Definitions. National 5 do like to ask about definitions, especially in the multiple choice section. So remember that. So if the current in a circuit doubles, the amount of charge that passes the points in a fixed time would also double. Just like if I said, if I got half of you running cross country, okay, if I got this half running cross country, I'd only get 9 of you, around the circuit passing a point. If I added in the rest of you, I'd get twice as many people passing this point. If you're all running at the same speed, okay. If you're like me and you're just walking it, then probably not working. And if the current in the circuit stays the same, the amount of charge that passes a fixed point in double the time doubles. Because again, if I just took this half of the classroom, made you run the cross country, and you're running at the same speed, then if I gave you twice the amount of time, you'd probably go around twice. So the amount of charge, the amount of people that pass me would double. Okay. So if a current of 1 ampere flows for 1 second, the amount of charge that has transferred is 1 coulomb. So charge is the current times by the time. Now you have to be careful with these questions because charge has to be in coulombs. Current has to be in amps. And time, which is the one that most people actually make the mistakes in, has to be in seconds. It's a nice equation to use, but you just have to watch your units. Do you want me to draw a triangle for rearrangement? Or were you okay with rearranging? I'll draw a triangle, but you don't have to use it. Okay, so I equals Q over T, T equals Q over I, and Q equals IT. Right, so what we're going to do is we're going to do a few examples of using this equation. Watch your units, that's all I'm going to say, because if you're making any mistakes with this equation, it'll be the units. So for example 1 is done for you. A current of 2 amps flows in a circuit for 60 seconds. So it's in amps, it's in seconds, that's okay. We don't need to change anything. How much charge is transferred? Q equals IT. 2 amps times by 60 seconds is 120 coulombs. Okay, they're not all going to be this easy. So the next couple of pages, questions 1 to 9, I would like you to have a go at. Now, please watch your units. So obviously, if it's in minutes, you need to change it into seconds. If it's in milliamps, you'll need to change it into amps. If it's in millicoulombs, you'll need to change it into coulombs. And the equations that you're going to be using, well, you're going to be using the same equation, but it might be in these forms. So have a go at the next few questions, please. Use your calculators. You can talk to people next to you if you want to. Giving you a few hints there just to remind you to change from milliamps to amps, you divide by 1,000. Change from minutes to seconds, you times by 60. I'm going to write the answers down, but please, so you can check them as you go along. Please don't just write the answers down. Please write down your working too. If you're not getting any of the answers that I've written down, please let me know and I will try and work through with you, see what you've done. Can I give you a few more minutes to finish these off? Please check your answers with what's on the board. Okay, one more minute and then we'll sort of quickly go through them. Please give me a shout if you're not getting any of the answers and we can check why. Okay, everybody, so question 2, you're just using Q equals IT, you don't need to change any units. So it's 0.5 times 150, which is 75 coulombs. Number 3, you got 4 amps, but you've got the time in minutes, so you need to change that into seconds. So it's 4 times 12 times 60, which comes to 2,880 coulombs. Number 4, you've got 5 milliamps and 2 minutes, so you need to change both of them. So you need to change the current into amps, so divide that by 1,000, which is 0.005, or 5 times 10 to the minus 3, times by 2 times 60 to get it into seconds, which is 0.6 C. 5, a charge of 12 coulombs passes through a lamp in 6 seconds. Calculate the current in the lamp. So the current is going to be charge over time. So 12 coulombs divided by 6, so 2 amps. Number 6, a charge of 14 millicoulombs passes through a lamp filament in 2.8 seconds. Calculate the current in the lamp. So it's charge, so 14 millicoulombs, so 14 times 10 to the minus 3, or 0.014, divided by the time, which is in seconds, so that's fine, which comes to 0.005, or 5 milliamps. 7, a switch is closed for 10 minutes and 3,600 coulombs of charge pass through the switch. What is the current? So current is charge divided by time. The time is 10 minutes. We have to change that into seconds, and that comes to 6 amps. Number 8, a current of 460 milliamps flows in a circuit. How long will it take for 2.3 coulombs of charge to pass? So that's time. So time is charge divided by current. So 2.3 divided by 460 milliamps. So 460 times 10 to the minus 3, or 0.46. And that comes to 5 seconds. And 9, a car headlamp uses a current of 2 amps. How long must the lamp be switched on for 10 coulombs to pass through it? So again, time is charge, which is 10, divided by time, which is 2 amps, so 5 seconds. Are there any questions from those? Relatively straightforward as long as you remember units. Okay, right, so I want to move on before you do a few questions, so I'll do a few more questions on these. So energy in a circuit. So Cells or batteries, we've already said this, provide the energy, and I want you to highlight that because that quite often comes up, to move electrical charges around a circuit. The potential difference or voltage mean the same thing. Potential difference is just the fancier word for same voltage. Across the supply is a measure of the energy given to the electric charges passing through it. It's measured in volts. So consider this mechanical circuit. So we've got a person lifting balls up, putting them on a rail, they're rolling down the rail, falling through a paddle wheel, and then rolling back along that rail to get back to the person. So the person continually lifts ball bearings from point A to B. They roll along the top rail, B to C, then C to D, turning the paddle wheel, they roll back from D to A along the lower rail. So thinking about our energy changes, when raised from A to B, what energy do the balls gain when you lift something up? Yep. They gain gravitational potential energy when the person lifts ball bearings up. And when the ball bearings fall from C to D, so that's through the paddle wheel, what is that gravitational potential energy changed into? Because it's moving the paddle wheel. Kinetic energy, yeah. So there is a loss of gravitational potential energy up here and not much down here. So there's a difference between the levels of gravitational potential energy. So there's a gravitational potential difference between C and D. Okay, so now we're going to look at a circuit and sort of measure the difference, see the differences or the similarities between those. So now we've got an electrical circuit. So we've got a cell, remember a cell is one of them, and then if you have more than one, it's a battery and a lamp, and we've got wires connecting them. So the cell pushes electrical charges from point A to B, just like the person was lifting ball bearings. They flow through the top wire from B to C, then flow from C to D through the lamp, making it light. So instead of them dropping through a paddle wheel, they pass through a lamp, and they flow from D to A through the bottom wire. So when pushed from A to B, the electrical charges, instead of gaining gravitational potential energy, they gain electrical potential energy. Supplied by the cell. When the charges flow from C to D through the lamp, I almost gave it away then. What is the energy change in a lamp? Electrical to light and yes. So that electrical energy gets changed into light and heat, just like the gravitational potential energy got changed into kinetic when it fell down. So there is more electrical energy up here and there is here. So there's an electrical potential difference between points C and D. I don't know why there's a missing word there. We say that there's a potential difference or voltage across the lamp. It's a measure of the electrical energy lost by electrical charges passing through it. Okay. So, potential difference, again, we've got another definition here. The potential difference or voltage across the supply is the electrical energy given to 1 coulomb of charge passing through the supply. So, I want you to highlight that. And when 1 joule of energy is given to 1 coulomb of charge by an electrical supply, the supply has a potential difference of 1 volt. So that top one is the definition there that quite often gets asked. So, in terms of this electrical energy, charge and voltage, if I had a cross-country run, okay, and I was standing at one point, and it was like a circular cross-country run, okay, and I gave a sweet to everybody to keep them going, okay, that passes me, okay, the total amount of sweets is the total amount of energy here. So 1 joule of energy is supplied if 1 coulomb of a charge moves across a potential difference of 1 volt. Okay, so I'm the potential difference. I'm giving 1 joule of energy. I'm giving 1 sweet to whoever passes me. If one person passes me, then the total amount of sweets in this cross-country run is just 1, isn't it? So there's only 1 person. I've just given them 1 sweet. If 2 people pass me, I'm still giving 1 out to each person. I give it to 1 person, I give another 1 to another person. The total energy in this circuit is going to be 2. So that's what it says. Something joules of energy are supplied if 2 coulombs of charge, so 2 people go past me, and I give them with a potential difference of 1 volt, I'll give them 1 each. So the total amount of energy in that circuit would be 2 joules. I'm just giving 1 sweet out to 1 person, to each person that passes me. So if 1 person passes me, there's 1 joule of energy in that circuit. 2 people pass me, there's 2 joules of energy in that circuit. So if Q people pass me, then there's going to be Q joules of energy in that circuit. So if 3 people pass me, there'll be 3 sweets in the whole cross country. If 7 people pass me, there'll be 7 sweets in the cross country because I'm just giving them 1 each. Okay, this is supposing they don't lap each other. Similarly, if I then decide that I'm not going to give 1 sweet to each person that passes me, I'm going to give them 2 sweets. Okay, so if 1 person passes me, I give them 2 sweets. There are 2 sweets in that cross-country run. Okay, 5 people pass me and I give them 2 each. There's going to be 10 sweets in that cross-country run. So this next one says 1 joule of energy is supplied if 1 coulomb of charge passes across a point of 1 volt. But if 1 coulomb of charge passes across a potential difference of 2 volts, so I give every person that passes me 2 sweets, then there would be 2 joules of energy in the entire cross country if 1 person has passed me. If only 1 person's passed me, but I've given them 2 sweets. If only 1 person passes me, but I give them 3 sweets, there'll be 3 in total. If 1 person passes me and I give that person 10 sweets, there's going to be 10. So there'll be V joules of energy if I give them V number of sweets. Okay, if only 1 person is running this cross country. So, in summary, the amount of energy is equal to the amount of charge, so the amount of people running past me, times by the amount of sweets that I'm giving out, the amount of energy given to them. So, the electrical energy is the charge times by the voltage. You could also write that as, I'll put that in brackets, charge is IT, so you could replace the charge and you could have ITV. So that is charge in coulombs, and that's voltage or potential difference. Remember, it's the same, 2 different words for the same thing, volts. So one example here, a charge of 600 coulombs passes through a 12-volt car battery whilst the car is being started. Calculate how much electrical energy has been transferred. Yeah, unfortunately, I forgot to say W stands for electrical energy. I think it's because it's sort of connected to work done. It's not particularly great, but E stands for something else, so we kind of have to say that W equals QV. The electrical energy is the charge, which is 600. It's in coulombs, don't need to change it, times by 12, which is in volts, don't need to change that. And that comes to 7,200 joules. Okay. Right, so I would like you guys to have a go at some questions from your question booklet now. So if you work your way, you probably won't get through all of them. Work your way through questions, page 1, questions 9 to 23, and then you can do all of page 4 as well.